least it starts going to feel like a physics class, but hey, heck with it. Here we go. There is a 10-pound weight, and you pick it up and you take it to the top of this cliff. And this cliff is 25 feet tall or high. Then the work done is 10 pounds times 25, and this is called 250, and the units are called foot-pounds. I don't know if you've taken a physics class when you have to find out what the work was done in lifting things, but that's essentially it. If you move a weight from a low position to a high position, you have to do work to make that happen. The amount of work is the weight of the object times the distance. Now, here's a very similar question, but metric. And you've got a 10 kilogram weight, and you pick it up and you carry it to the top of a 25 meter cliff. The work done is 10 times 25, but there's another number involved. What's that other magic number? And it's a gravity constant.
9.81.
And you just have to remember that when it's metric, you need 9.81. It's the, what's it described as? Is it the force due to gravity?
Yeah, it's the force of gravity on a specific part of how close you are to Earth, and it's just used as constant there because
it's pretty much the same as long as you don't climb up a mountain.
Yeah, basically. Otherwise, it's slightly changed.
So this number is definitely noticeably different. And the units this time are, I think, is it kilograms per meter squared? Newtons. I think they're called newtons. So I'll just call them newtons. I won't get too caught up on the units. I think the homework sticks the unit label at the end for you. So you just need to fill in the missing number. So our first question is very trivial. You're going to get a rock or a weight and you're going to move it up 10 feet or 25 feet. And if it's feet and pounds, you multiply it. And if it's metric, you multiply it with an extra 9.81. And you do it that way because basically metric units need that extra constant. So far, so good. It's not actually that much happened yet. So I'm going to show you what the two questions that look similar to what we've just done look like. So we can kind of move on. It's a little bit bigger. Okay. Oh, did you know it was a 310-pound gorilla, not a rock? And it climbs a tree 29 feet high. And you're being asked to find the work done. Well, the work done is basically whatever 310 multiplied by 29 feet is. And then they give you a trick question. It takes 10 seconds. What's the work done? And then it says it takes 5 seconds. And what's the work done? And the answer is, that's because it's a trick question, is it's the same blinking answer in each case. Work doesn't care how long it takes. So if it takes your little brother 5 months to cut the grass, it's still considered one grass cutting amount of work, right? The amount of work has no relevance to the time it takes. So that's really a trick question. In question 2, do you see that the units are now metric, kilograms and meters? But they have been nice to you. Oh, slightly different from what you got, but that's just an accuracy thing. they're telling you just to use 9.8 instead of 9.81. So if you wanted to do the particular one I've got here, you do gravity, which is 9.8, multiplied by the weight, which is 280, and then you finish with 6 meters. Whatever that is the answer. Okay, so those questions have nothing to do with calculus. They're just an intro to calculating work, right? Questions involving how much work is done. Are we okay with those questions? It's pretty much multiply some numbers. You don't even write the calculation down, don't you? Just write down what the answer is and call it good. Now we're going to do work questions that actually involve calculus. So we're going to introduce you to a function called the force function. Now, the force function is basically how much force do you need at some position X. So you can imagine that you might be using a lot of force when you're pulling up a very steep hill, and then the hill isn't so steep, so you use less force, and so on. So the position X, a certain amount of force is being used to move the object. And if you want to know what the work done in moving this object with a force function of f of x from position x equals A to position x equals B, it's just that. Oh, so the integral of the force function from start to finish is the work done. So suppose I give you a force function, and this force function is called a variable force, and it's 8x to the negative 2, okay? And you're going to move this object from the position when x equals 1 to the position when x is equal to 5. And you're being asked to find what work would be done in moving this object using this force function. And it's as simple as from 1 to 5 of that guy. Now, considering some of the things we've done over the last few weeks, that's almost a baby question, isn't it? I mean, there's virtually nothing to really work out with. You know, if you tell me who he is, which you did, and you tell me who these are, which you did, then I just put them together and I've got to work. I can do my calculation. It's a power rule, so I guess I better be careful. If you add 1 to that power, what's the new power of x?
-1.
Correct. Do you know the mistake that I have made, and some of you might? -3.
Mm-hmm.
Right? You're adding 1 to -2. Now, if you divide by the new power, you get that. I would suggest strongly that you write it in this format. It's just easier to do calculations on your calculator, right, when you've got fractions, than if you do -1 powers. Now, it will work with -1 powers, right? You're going to get an answer, but I would suggest strongly that you turn it into this. So let's see what that gets. You plug in 5, you get this guy. Take away, you plug in 1, you get this guy. So what's that? -8/5 plus 8. And I'll go to my calculator. And I'll do a -8/3. Then I'll add an 8. And I'll turn that into a fraction. And the answer is 16/3.
It was 8/5 and not 8.
Oh, yes. Well, if it was thirds, that would be the right answer. And since it's not, I will redo it with the right value, 8/5, add an 8, and I'll turn that into a fraction. And it's 32/5. And do they give me units in this? They do. So the units are foot-pounds. But you don't need to worry about that because in the homework, you put the number there and they've already done the label at the side. So you don't need to put the label in the foot-pounds part. You just put that guy. Or I guess in this case, you could do 6.4. I just like fractions, exact values. Does that feel pretty straightforward? If you give me a force function and you tell me from x equals to x equals, I should be able to tell you the work done in moving the object from here to here, applying this force function to it. Now, what makes this more realistic is if you imagine the classic kind of physics question, doesn't the object always weigh the same amount? And so the force you apply is the same all the way through its journey. That's why you can simply just multiply two things together. They're both fixed constant numbers. But you can see in this world, now that we have a function, a force function, where the force can change depending on where you are. Can you imagine dragging something up a hill and it's got a leak in it? So as you drag it up the hill, it's lighter. So the amount of force would change through position X. More realistic, essentially.
Can I ask you a real dumb question?
I like dumb questions because I'm pretty dumb myself, so go for it.
You probably already covered this, but nope, never mind. I just figured it out. Sorry.
I am no. I'm taking credit for this. Do you notice how good I am at teaching now? I used telepathy. Did you see that? I read his mind, and then I told him the answer, and he thought it was his idea, but it was me. I am that good. So you lot better tell my boss how amazingly good I am at answering questions now. I can do telepathy. And Sean, I can, so I'm reading your thoughts right now. Are we good?
Reading my extreme emotions of gratitude.
God, I'm having a fun day today. I have no idea why I'm in a funny mood today, but it's working, so who cares? The next question I'm going to show you because it's a visual one and it's from the homework. So I'll just basically tell you how you would solve this. What you have here is the position. Maybe you're pulling some object, 1 meter, 2 meter, 3 meters, and then the force function is here. Now, can you see that at the start you got no force, and then isn't it getting harder and harder to pull, and then you get to the 8 meter mark, and then it's actually pretty constant. That's virtually a force position function, right? So if you want to know what the work done, aren't you finding the area under this curve? Now, don't go crazy and make your life hard. Can't you just find the area under this curve by making it whoops, I can't do that, making it a triangle and a rectangle? And can't you just find the area of the triangle as a half base times height and the area of the rectangle base times height, right? Length times width. So let's do the rectangle. 8, 10, 12, 14. Isn't that 8 units long? So that's 8 meters. And what, 54 newtons tall? 8 by 54, whatever that number is, that's the work done for that bit. And for this little guy here, won't it just be half base times height? And you'll probably get some really ugly, 3,900 kind of number out of it. And I've just figured out what the units for work are. I said they were newtons. They're actually called joules. Right? Doesn't make one darn bit of difference. It's the same answer, isn't it? It's going to be the same number, just the units are called something that I didn't call them. Any questions about that? So if I gave you a shape like this and said, look, how much work done in this position force diagram, won't you just say, oh, you want the area under the curve and just do it through geometric means? Triangles and rectangles added up. Get a nod on that? Are we good? We are good at it. Right. Then we're now moving on to a different situation. We're still calculating work, but we're going to look at work and stretching springs. So I want you to imagine that you've got a spring. That spring has a thing called its natural length. So if you just left it sticking to the side of a wall, I know, pretend it's not drooping, pretend it's strong enough to keep horizontal. It has a particular distance called its natural length. Let's say that the natural length of this particular spring is 0.1 meters. So it's a pretty heavy duty spring, right? I know, kind of springs that tanks might have, whatever, right? Big spring. What a guy called Hooke discovered, and it's called Hooke's law.
Yeah, I remember this.
Ah, some of you have done this.
Yeah, I had a class for physics a couple of semesters ago.
Now, what might be different here is that the physics class might do the exact same question and get the same correct answer, but they may do it through formula, and we're going to do it through integration. So there'll be a bit of a different approach, but the same destination. Now, what you got to imagine is that this spring gets stretched. And the distance extra that you stretch it is x. Right, so you might stretch it 0.3 of a meter, you might stretch it 0.01 of a meter, but you'll stretch it beyond its natural distance. Hooke, or Hooke's law, discovered what the force function is. And it's a very simple rule. If you want it in the way physics people might say it, the force is directly proportional to the distance beyond its natural point. It's called kx. You're nodding, Michael. So far we're on the same boat. Is that the way they would have described it back in the day?
Yeah, more or less.
Right. Now, this k is a fixed number, right? It could be 10, it could be 0.003. If you want to think what is k, do you know if it was a big, massive, thick spring, it would have a huge k value, right? It could be 50 or 150. And if it's a slinky kind of spring, the k would be tiny. It could be 0.02. So this missing number is basically a number that measures the stretchability of a spring, right? How hard it is to stretch it, right? Big numbers, really hard spring. So you would probably expect a big k value on springs and shock absorbers, right? You wouldn't want a slinky as the spring in your shock absorber, right? That wouldn't do anything at all, right? It wouldn't help as part of that process. And what he discovered then is that. Now, if you want to find the work done, then it's the integral from a to b of the force function dx, which is nothing new because everything else is the same. But in this case, a is the position after the natural length. At the start, and B is the position after the natural length at the end. So you might say, well, what the heck does that look like? So let me put a story with some information in it. Imagine you've got a spring and the natural length was 0.1 meters. And you want to know how much it takes to stretch it from here to here. And A is 0.2 meters and B was 0.5 meters. So we're not even stretching it from the beginning. Can you see that what we're saying is that this is another 0.2 of a meter? So it's already been stretched before, right? So we've already got this pre-stretched spring starting at 0.2, and we're going to stretch it another big chunk, right, to 0.5. So can you see that the A and the B are a little bit, you got to think about them. So that's what that would look like. So a whole story coming up here. This is question 5 or like it. And it says a force of 14 pounds is required to stretch a spring um, 4 inches beyond its natural length. Now, what it doesn't say, but you will always do that, is that once they tell you this, you will use this information to find K. So this is only the first part of the question, but I'm going to stop here and we're going to find out how to find this mystery K. So the force function is K times X. It takes 14 pounds of force to move it 4 inches. And here is a little stinker. It's feet and pounds, or it's meters and newtons, right? I'm sure you've had physics where they say units, 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 right? So the units of the day are feet and pounds, meters and newtons. Right? So it's not 4 inches that goes there. Isn't it 1/3 of a foot? 4 inches is 4/12. So 4 inches. So 14 is 1/3 K. Now it doesn't take much, does it, to figure out who K is? What would I do to both sides to find the magic K for this particular spring in question 5?
Yeah, you
Just
divide it
multiply
out.
by 3.
Well, it'll be dividing by 3 or multiplying both sides by 3. I guess that's the choice, but only one of them's right.
Multiply by 3.
Right, or divide by 1/3, which is multiply by 3. 342. So I think that's quite a big K value in the spring world. So it's more likely like a spring in a truck kind of K, right? Now, that's part A done. That means I now know my force function, but it's not going to be K times X anymore. Once you know who K is, don't you know the force function? And then they're going to be typically the second half of the question, which is how much work is done in stretching the spring from here to there, right? That kind of question. So this is what it looks like in question 5. How much work is done in stretching it the spring from, a lot of words here, its natural length to 6 inches beyond its natural length. Well, the work done is the integral of the force function from whatever start to whatever finish. In this case, it's starting at its at 0, right? It's starting at its natural length. And we're stretching it 6 inches. Will this guy here be 6, or will he be some other number? Units, units, units.
It'll be 1/2, right?
Correct. And the force function is 42x. And that's going to be 21x squared, evaluated. And plug in a half, you get a quarter, so 21 quarters. And the units here are feet in pounds. Units, units, units. Right? Imagine the question had the same start, so this is not changing. But they asked you this one. How much work is done in stretching the spring from 9 inches beyond, beyond its natural length to 2 foot. Now, the work done is going to be the integral of this guy, right? You got a start guy and you got a finish guy. The smaller number, the start guy, is 9 inches, 9/12, 3/4. The finish guy is 2 feet beyond its natural length, 2. And then you do the usual kind of integration. Are we okay with that process then? First, you got to get K, and then you do an integral of the force function to find the work done. And the work's going to be taking a spring from here to there, right? From an A to a B. And make sure everything's in feet. Units, units, units. Are we good? Right, let's look at another one. And this one is like question 7. And it's going to take 6 joules of, right, a force to do it from 30 centimeters beyond its natural length. To 47 centimeters beyond its natural length. Now, essentially, it's the same kind of question, but you have to work on it a little bit more. This piece of information here is going to get me the K. But the way this information here is set up, it's not so obvious how to get K. The first time, they told me this number and I could use my formula. But in this case, they told me the work. So I'm going to set this guy up like this. And then I'm going to call 30 centimeters, nothing 0.3, 47 centimeters, nothing 0.47. This fella, I'm going to call it kx, dx, and the work done is 6. So do you see in this case, the way I'm going to find k is much more awkward. I can calculate everything here, and I should be able to figure out what k is. Yeah, let's see how that works. The first step is cosmetic. Since k is just a constant, can't I bring it outside the integral just to get rid of it? You know how I've done that with pi, for instance, right? It just gets in the way. Power rule. And do not get worried by the fact that a lot of these questions are going to be downright ugly numbers. Add 1 to the power, divide by new power. Plug in 0.4.
0.47.
Thank you. So 0.47 squared, take away 0.3 squared. Right, I'm going to do this guy, and I'm not even going to attempt to make a fraction. I'm just going to figure out what that is as a decimal. So here goes. Not quite sure what you can see, actually. Yeah. I hope you've been seeing this all the time. So here goes. 1/2, that's nothing 0.5, times 0.47 squared. Subtract nothing 0.5 times 0.3 squared. And I get the answer 0.06545. Okay. What do I need to do to both sides to find k?
Divide by that.
Now, the fact that the numbers are ridiculously ugly does not change the math. If I'd said 6 is k times 9, wouldn't you just divide both sides by 9? I wouldn't even give it a second thought. It's just a weird decimal that's thrown us. So let's see what this fellow looks like. 6 divided by 0.06545. And the answer I get is about 91.67. So far, so good. Which means that after a lot of hard work, I now know who k is. So I now have my force function. Oops, time. So what kind of questions do they finish with? Well, they'll ask you things like, how much work done is moving it from 38 centimeters to 43 centimeters, and they want the answer to 2 decimal places. Okay, work done, the integral from A to B, force function. 38 and 43 are not 38, and they are not 43, because I need to turn them into meters, right? Meters, kilograms, feet, pounds, right? That's the units that we work with. This horrible guy. I think it's probably the first time we've ever had an integral where everything's just ugly, right? We normally get 0 to 4 or 5x, right? That's the kind of question we're used to. I don't really care that it's ugly. I do the same thing. It's a power rule. I'm just going to write it like that because I'm not bothered. I'll let the calculator figure it out later. and it's going to be evaluated at this horrible decimal and finish at that horrible decimal. So it's going to be 91.67 over 2 times 0.43 squared, take away 91.67 over 2 times 0.38 squared. And if I've ever seen a question that needs a calculator, that's it, right? So here goes. .67 times 0.43 squared divided by 2. Take away 91.67 times 0.38 squared divided by 2. Oh, shooting space. Must have hit something funny there. Try again. 91. Oh, I know I did. 0.67. There we go. 0.43 squared divided by 2. Take away the same guy. Ooh. Yeah. Do you know there is a rule that I have just broken? Everything I did is correct for what I thought the question was. And I thought the question was 30 centimeters to 47. And that's why this was these two numbers. Now that I go back and read it, its natural length is 30, and you move it to 47. I'm not going to redo this blinking question again, but right there is where I screwed up.
So would you say from 0 to 47 instead?
Not even that. Another 17 centimeters
Oh,
beyond the 30.
yeah, makes sense.
Now, can we just pretend that this question was what I thought it was? In which case, this is the correct answer. When I looked at the answer they got, it wasn't the same, and I was thinking, okay, where did I screw up? And I didn't screw up on the math. I managed to screw up on what I read the first time I read it. I read it from 30 centimeters beyond to 47. Instead of its natural length is 30, stretch it to 47, right? So natural length is 30 means you start at 0, and 47 is 17 centimeters later. So it's still correct if it was my question. Oh God, time. I get time to fix one more in. We do, because it should be a quick one. Question 8. The work required to stretch a spring 1 foot beyond its natural length is 15 foot-pounds. So force function is kx. This number is 15. This number is 1. K is 15. That is so much nicer. Can you see this? Are you seeing this on the white screen? Right. Now, they then say how much work is needed to stretch it 6 inches beyond its natural length. Well, the work done, A to B, force function. To stretch it 6 inches beyond its natural length, 0, 6 inches. Right, that tells me 15x. So 15 over 2x squared, evaluated at 0, evaluated at a half. A half times a half is a quarter, 8. 15 eighths is the answer. Oh, it is such an easy question compared to the last one. It's pretty much, it was plug and chug. And God, look at how nice the K is. Okay, say hi, everybody. That's pretty much us at the end of today. I look forward to hearing some really good jokes. Evan, you're going to find me a Norwegian joke for tomorrow.
All right, you got it.